Welcome to Lecture 14 of Comp 19512 Introduction to Computer Systems. Today we're going to talk about a number of issues relating to outside of the embedded system or personal computer. And they're to do with how you might communicate with other systems. So in that area we're going to look at how you might communicate, and then to understand this we're going to first look at how you might physically do that. What sort of connection would you have? Is there different types? Then we move on to look at rules. Now these rules are actually, the naming convention for these is called a protocol. So when you're looking at a number of different rules, they're called protocols. With respect to receiving and transmitting data, it's called data transmission protocols. The next thing we look at with respect to connecting up systems outside the computer to talk to one another is how they're connected. These are called topologies, sort of maps, and they're connected into different networks, so we're going to look at network topologies. Then we look at small networks, and then we look at large networks. So one of the important things we look at is that local area networks are the small networks, and they have a set of rules which are called protocols. The larger networks, and there is one in between these two, called a wide area network, and they have a set of rules as well. And then how is this larger system, physical larger system, which is a set of networks connected by backbones, the internet, put together with these two? Then we see that these interaction through protocols or rules, and there's layers of different interaction. We'll talk about what this means during the lecture. So if you remember, we should have in a few more weeks a feedback session with respect to your coursework. So I think in the last two lectures at least I've mentioned this, so I'm not really going to say much more in this lecture, except you've got to register on the web for this feedback personally yourselves. So we're going to start this lecture with the standard Q3s. We're going to look at last week's lecture when we looked at operating systems and where they all begun. And well, let's look at the first Q1 then. And the question is, what is the common sequence used in batch processing? What are the basic three steps that batch processing follows? So I'll give you a minute to think about that. Here are the basic steps. The first one is the operator, who would be a human operator initially, would be putting the information together, gathering it together, the cards or the tapes. And then once you've got this set of cards, each set of cards as a program is called a job. And then a number of jobs are put into a batch. So that's what the operator does first. It puts the jobs into a number of jobs called a batch. Then the operator puts this whole batch into the computer entry system. And then these jobs, which are a set of jobs as a batch, are run through the computer, and then the outputs to each job is explicitly outputted from the computer. Let's move on from there. And we had another issue with computers and different types of computers, which is addressed in question 2, and that is, what is time sharing called on a multi-user system? So you have to remember, what was the naming convention? I'll give you a few seconds there. So this type of time sharing on a multi-user system was called multitasking. Now let's move on to the next and final question in Q3. Bit of a longer question. You have to name the main components of something, so let's read it out. The shell provides the interface to the operating system. A kernel may be viewed as part of the shell. Name 5 of the main functions a kernel performs for an operating system. So I'll leave you a minute to think about those 5. And they are managing files, so a file manager, and then each device has a different method of interacting, and they're device drivers that perform this. And then the memory also needs to be managed as well, for swapping in and out memory segments or pages, so we need a memory manager. And then the CPU is managed as well by a scheduler and a dispatcher. Scheduler schedules up the different programs to be run, dispatcher dispatches them and swaps out programs onto the CPU. And finally, the bit we're going to be talking about more about this lecture, which is when we're interconnecting to subnets and then major networks, we need a network manager. So again, just a quick reminder about the feedback again. So I'll move through that quickly, and again the process you should have seen by now for the whole process of how you undertake the feedback and how you register for an email with a particular time slot in the feedback times on Blackboard. So I'll leave you with that. If you've done that, well done. If not, you could probably might be useful getting some feedback for your coursework. This is basically the last lecture in the series. At the end, after the Easter break, there's no lectures, but we will be giving tutorials happen actually not next week and the week after. We don't have any lectures, but we have tutorials. So there we're going to work through some mathematics and some processes that you'll need in the exam. So if you're wanting to achieve high marks in the exam, it would probably be worth coming. Again, note about the type of feedback we're going to have in the feedback session a bit later. Now let's move on to the lecture itself. So again, in the first lecture, 13, Networks 1, we're going to look at communication. Maybe the first thing we're going to look at is how this is physically done, maybe even physically connected. So how would we do that? The next thing we look at is a set of rules. So protocols are rules for actually either sending or receiving, transmission of data. So how are these undertaken with these? We'll look at different rule sets for doing that. Then we look at different connectivity, so network topologies, different layouts of interconnections of different nodes. So we look at those. So this diagram here is a very simple network. It could be called a toy subnet, and maybe a really small local network. And on it you've got a client, which would be these two computers, and a server which might be providing files or applications and users for these systems. And the data is sent across this network. So during this lecture we're going to find out there's different type of networks and different ways of sending information through it and round it. So we'll talk about that in the lecture. So the first thing we're going to do, as we've already explained in that little diagram, is we're going to look at small networks. So these are called local area networks, LANs. Then we're going to look at a bigger network, and it's totally different the way it transmits data. These are doing it in certain ways, which we're going to talk about in this lecture, but this wide area network does it in a total different way of transmitting information. So we're going to see they're totally different in the way they transmit information. Now we move on from there, and we look at this idea that information we've looked at mainly today, previously as well, has been like this page. It's been on a page, it's been presented as a block of information, and maybe that, if we look at our von Neumann computer, is sent in a bit parallel way. So there'll be 8 bits of information. But now we're going to send information a bit more differently, in the sense that we're going to send it one bit at a time, and this is called serial data transmission. So we're going to see what this means and how the data is transmitted. The next thing we're going to look at is seeing that actually when it is transmitted, it's changed from a bit parallel 8-bit to a bit serial, and that this might be done with digital signals. So we're going to look at what a digital signal is explicitly, have a look at a diagram and explain what a digital signal is. Then we move on to talk about, well, in reality we cannot send a digital signal across free space. So that means the wireless transmissions and Wi-Fi is not digital. You might have thought it is. The main reason for this, bit beyond the scope of the course, is that if you ever worked out how to transmit a digital signal, you should go down the patent office and patent it, because it's nearly impossible. And the reason for this is, well, think about how you transmit that transition from a 0 to 1, and how you'd simulate that to do that sort of transmission change from a low to a high very quickly. And it actually requires a very, very wide bandwidth, so it's not done. But what is done is simple narrow bandwidth signals, which are called analog signals. So we're going to look at a number of methodologies for putting data onto analog signals. So this terminology used for doing this is modulate, change their height or their frequency or their phase. So this illustrates how amplitude shift keying works, and it basically says if you're a 1, you allow this amplitude on that sine wave. If you're a 0, you have another amplitude. Whereas frequency shift keying does the same, but with frequency. For a 1 you have this frequency, and for a 0 you have another frequency. And phase basically shifts the phase of the signal depending if it's a 0 or a 1. So we'll see how these modulation of amplitude signals, like amplitude shift keying and phase shift keying and frequency shift keying, all modulate different components of an analog signal to transmit digital information by overlaying the digital information onto the analog carrier or data channel. So then we look at how we transmit information, mainly in this sort of area, in the wide area networks, when we break it down into smaller components. So this page is made up a lot of information. You couldn't actually realistically send this page all at once. The page has to be broken down into smaller blocks, and these small blocks are called packets, and then these bits of information called packets are physically transmitted. And you might realize, well, does that need any overheads or rules? And the answer is yes, it needs both rules and overheads. The overheads are, well, you need to know where each packet is in this, if it's transmitting this page, where they are. So they might have a sequence number to tell you where to put it back together, so you get this bit of information rearranged in the right order. So the next thing then is, how do we connect up these different networks? And is there different connection or connectivity for each network? The answer is there is. Local area networks have a number of different connectivities or network topologies where they connect them up differently. We've already seen one, which is a bus. So we've identified one. There's at least 3 more we're going to talk about. So we're going to identify these and look at some typical different structures called topologies of networks. So that's what we're going to talk about during the first half of the lecture. So let's think about networking. So what does this mean, this idea, this word? Well, what it actually means is we're going to connect and allow a number of computers to communicate, and we connect them to a network. And then we say when we're allowing a lot of computers to communicate across this physical entity, a network, we call it networking. So there's some naming conventions. So what does it enable us to do? What can networking facilitate? Well, the first thing you can do, as we saw on the very first diagram on the first page of the lecture, is you can have a very small network with a client, 2 clients and a server, so you can share resources, share files, share applications. So you could have a print server on the server, and the other 2 client computers could use it. And that's the norm, and you've probably seen that already in a number of labs you've been in already. The other thing you can do is you can actually move information around this network. You can transfer it from one client to another, from one client to the back-end server. So a network allows you to move things, so transfer information. Also lets you send information like email. That's an example. So what do these networks do, and what does networking enable? What they're actually providing is a number of services. So services enable machines to have extra functionality. So if you have one machine not connected to a network at all, you couldn't really use a printer. So you couldn't communicate with other computers, which are then in turn communicating with their users. You also couldn't use, if it was a single computer not connected to any other things, printer or a client-server configuration and the server's connected to a printer, you couldn't print. So what the network and networking enables is services provided by other machines. Maybe the back-end server provides a number of functions that single client computers could use. So this is really what we're talking about. We're talking about interaction, sharing information, transferring of information from one computer to another. We're also talking about sending emails from one computer to another, which is again transferring information. So now let's name two different types of networks. There's small entities which are across rooms. There's larger ones which we're going to see in a minute. So let's first talk about the small network. And as it's local, it's called a local area network. So it's local. Let's see what specifically it means. Well, we've already seen this diagram before, but now we're going to name some components. So the first thing, we're going to name the nodes. These are nodes that connect up this subnet. And this is the main network link. And here's the clients connected to the nodes and the network, and maybe a server. So what does this local area network enable us to do? Well, first thing to realize is the differentiator here is the local area network means the computers are physically close. They're physically near to each other. So an example of these, as you've probably seen in labs, is a local network in a lab or a number of labs. And the school actually has these and runs local area network. So that's an example of a small network that's physically close. In reality, these local area networks, well, there isn't one across our whole building or a couple of buildings. There's a number of local area networks. And they're connected together. This connectivity, depending on what the networks are, different types of networks, we'll name some conventions used for connecting them in a minute. Next thing is if you're looking at a much bigger network, maybe across a continent. So you realize that that is transmitting data over longer distances. What are these called? Well, these are called wide area networks. They cover physically a wide area and they're not physically close. So what tends to happen with this, and the naming convention used for this, is the connectivity is connecting remote situations or areas. So here's an example of that. Maybe connecting a computer in Manchester to London. Okay, that's the remote locations, and they're wide area networks that could be viewed as connecting the two. So is the internet a wide area network? Well, maybe not. Maybe the internet is a number of wide area networks connected together by things called backbones, which are actually fiber optic communication channels. So we might talk about that a bit later. Now what we're going to talk about is some naming conventions and some views of what's actually happening with relation to connecting two computers which need to communicate, and these are some issues we need to address. First thing, they're connected by physical media. That means cables. Different types of cables are used. And the way the information is sent along these cables is structured or is sent in a particular way. So the issues are what type of cable and which way is the information sent or structured to be sent down this channel or physical media. And the third one is, if we look at the network, how is that put together? So we've got how are the connections physically put together as cables? How is the information structures as components of data? How many are there? How many bits are there? That sort of thing. And then, what does the actual physical network look like? How is it connected together? So these structures are called topologies. They're really sort of maps. They're diagrams that show how these networks connect from one node via a media or a link to another node. So here's a very simplistic top-level view of a network. The network in here is just starred to say it's a particular network, and two computers connect to the network. So this is a very basic top-level view of a network. This is a more detailed view. We're going to talk about these subcomponents in a minute. This is really what a network of networks is. So it's a network of local area networks connected up in certain ways. Okay? So we're going to find out in a minute that these networks have particular ways of transmitting information from one of these units to another. So we're going to see their rules or protocols and talk about how this might be done, and then name some of these interconnections between these two in a minute too. So the first thing to look at is then how these two computers may be connected. There will be a physical connection, and it normally will be a piece of wire. Normally it will be two pieces of wire twisted together. That's a particular type we'll see in a minute. So let's suppose it's a single wire, just for the sake of these examples we're going to talk about. How would we transmit data from computer 1 to computer 2? Well, this moves us into how you communicate over a single wire. And there's two basic methodology. Many years ago, maybe 50 or more years ago, there was only really one. There was analog, and everything was done in analog. There were analog computers, there was summers, there were differentiators. They transmitted one type of signal, and that was called analog. The other type of signal that came along and superseded it was digital, normally two levels. So let's have a look at these two then. This is a typical analog signal. It's a sine wave of a particular frequency and amplitude. So this is an analog signal with continuously varying amplitude, with a number of levels which are continuously varying between a minimum and a maximum, between a particular sine wave, one repetition and the next. So they keep repeating. So that's a sine wave, and it's an analog signal with a number of characteristics. So the first thing to realize about this is it's time varying. If you look at it, its amplitude would start here and vary to a low and then go to a high and then repeat again, continuously varying in its value. So the variation would be in its voltage level. The voltage would vary, and that current level would change it continuously. So this might be sine of a signal, so it might be a sine wave that it's varying in relation to. Whereas digital data has a different representation. It only has two levels, 1 and 0, and that's all. So it still can be time varying, but the terminology used is it's discrete. It's not continuous, it's either in a 1 high level or a low. That's all it can be in. One of two voltage levels. So two values, a 0 or a 1. And that's how we store information in digital. Let's move on from there to show you how an analog signal might vary. So it's varying continuously, and the signal is varying in level over time. So this x-axis is time, and this is voltage level. So as we can see, the signal takes on any voltage level between a given range over time. So these typical analog signals are either music or a clock. So I'll just give you an example of an analog clock, and you can see it's varying over time between a certain number of continuous values as it goes round. The other example is music, and that used to be always analog signal. And these signals were then amplified, and the actual magnitude of the signal would be basically changed in size, so it'd be increased, amplified. So now let's look at the use of signals. First thing to realize is in our previous lectures we've talked about only using particular types of information, and these have been binary, probably 8-bit information, and this normally was talking about implicitly probably the concept of digital information. So we're talking now about a signal can be digital in nature, and we could transmit digital information, we've already implicitly talked about that, because when we're doing a memory read or a memory write, we transmit information from the processor to the memory for a write, or we transmit information from the memory to the processor if we're undertaking a read. And nominally, implicitly in that, we've talked about digital signals. However, it's not always possible to use digital signals in communication media. So we tend not to use them in telephone lines. And in fact, we can't use them for telephone lines. So that copper cable, if you look out your window in your house, that's connecting your house to the local junction box, is probably a copper cable that is transmitting an analog signal. So sometimes digital signals need to be encoded as analog signals to make and use the physical media to transmit the signal. And that is the case. You have to recode them or encode them from a digital signal to an analog. And when they come back, when you receive them, you decode them the other way from an analog signal to a digital. So let's start looking into this then, this idea of different media for transmitting data, which tends to be transmitted as an analog, continuously varying over time signal. So what we've seen now is we cannot, and it would be far too expensive to have 8-bit buses going out from your house. Instead of one single cable coming out, you need 8 to represent 8-bit words. So you couldn't do that. So buses over long distances are not possible. Over short distances on silicon or on motherboards, it's quite easy to have 8-bit, 16, 32, 64 or even 1 to 8-bit buses of parallel wires to transfer bit parallel information. Normally this was done in 8 bits wide, and these were transmitted 8 bits at the same time down an 8-bit bus or a 16-bit bus. This can't be done over larger distances, so we need to use a single wire. Then what we have to think about is, well, in that case, if we've got 8 bits, how do we send them over a single wire? And well, let's leave that aside for a minute and actually first say, well, this type of transmission is called serial data transmission, where you're sequentially sending information but on a single wire. So we're going to say that that has to be done in bits. So let's go and look into this in a bit more detail. Now this diagram shows you in real time how bits are transmitted one after the other. So this is really how a single channel, single wire, transmits digital data. Normally it would be in one state. Maybe nothing has been transmitted and it will be in a high. Then it needs to transmit something to tell the receiver at the other end that after this signal, here's the data. So we need a start bit. So we go from a signal that's telling you nothing's on this line, this single wire line, to a signal that tells you something is now going to be sent on it. And this is called a start bit. So now let's run through the data and see how each bit, single bit, follows another in serial data transmission. Let's look at this then. So you can see what's happening here is we're sending a pattern of bits 1, 1, 0, 1, 0, 0, 1, 0, one after the other. And the reason I'm making this happen again and again to physically show you how a single bit is sent one after the other sequentially. And as you can see, this is serial transmission. Now when it finishes, it goes back to the nominal state and the receiver knows, okay, I've picked up 1, 2, 3, 4, 5, 6, 7, 8. I've picked up a byte. It might be serially, but it's picked up a block of data after being told here that start of transmission, serial transmission is occurring. Okay, so this is serial data transmission with a start bit, and normally the line will be in one condition before it changes. And here the ones and zeros are coded exactly as ones and zeros might be. 1 is a high on this line and a 0 is a low. So this is just showing you a serial transmission changing over time. Now that's looking at mapping these from one type of signal ones and zeros, digital, to another which is continuously varying. So we can't support particular types of transmission on particular types of media. So you can't support digital transmission on telephone lines. So we also have to realize that we might have to do this change of type of data transfer from digital to analog to transmit through free space as well. So let's think about that then. The first thing to think about is that these two distinct values, 0 and 1, where the signal must stay at a particular level for a period, need to be transmitted. The way this is done is particular types of hardware called modems transmit these signals. So there's a bit more to it than I've just shown you. But basically what they do is they take this signal we've just seen on the previous slide, which performs a bit parallel to bit serial conversion and digital, and they map it onto or modulate a sine wave that's continuously varying. So I'm going to show you how that's done in the next slides. But what they have to do is change the signal from a digital signal to an analog signal. And this is going to be done by transmitting different types of sine waves. So let's have a look at this. So let's first have a look at the characteristics of a sine wave. And again, I'm going to show you it varying continuously a few cycles. So here a sine wave varies from a minimum to a maximum, continuously varying over a range. And again, showing you it's varying. And one instant we can see a period where it repeats. And here we've got a particular amplitude. So this is a sine wave varying between two different amplitudes, continuously varying over time. So this is how a carrier, because this is really a carrier, would be used to transmit digital information. So how do we change this? Well, if you look at it, there's a number of characteristics we could change. One is we could change this amplitude or magnitude of this. So we could change this height depending on whether we want to send a 1 or a 0. So that's one type of modulation. We could also change this interval or frequency. So a period is related to a frequency, so we could change that, have two different ones for ones and zeros. Then we could change where this starts, its phase. So that's a hint at how we could start mapping onto modulating this. So that's how we're going to look at it then. We're going to think about how we use sine waves to carry digital information. We're going to modify the sine waves and overlay on top of them either information that tells you with this particular type of sine wave it's a 1, with this other type of sine wave it's a 0 representation. So this is called modulation. So how we change the sine waves is we modulate it. We either modulate the height, the amplitude, we modulate the frequency, we modulate where it starts, its phase. So let's go over these three different types. First type is an amplitude can be changed. So the maximum height of the signal. So this is called amplitude shift keying. Now let's just explain what these three words mean. In fact, it's only shifting probably between two levels. So the amplitude shifts from one level for a 1 to another level for a 0. So it keys on, if it's representing a 1 or a 0, the amplitude changes from a 1, that amplitude, to a different amplitude for a 0. The next one, the frequency, is exactly the same, but it modulates or changes the frequency. So it shifts the frequency dependent on if it's a 1 it's transmitting or a 0. So the frequency for a 1 could be double that of a frequency of a 0. So it changes the period. Okay. The final thing it does is it changes the phase, when the signal starts, if you like. So let's go and look at some diagrams of these, and hopefully they'll explain a bit more explicitly how this modulation is undertaken by changing the signal height, the signal frequency, and the signal phase. So here's a signal which is a serial signal of 1, 2, 3, 4, 5, 6 bits, and they're sequentially transmitted in bit serial. We're going to map this onto three different modulation techniques: amplitude, frequency and phase, and see what happens to the sine waves when you amplitude shift key. So the first one is here, ASK. So for a 0 it's a low amplitude carrier, then it switches to a higher amplitude, then it switches back to a lower one for these two zeros, then it switches to a higher amplitude or size of the carrier signal. So that's amplitude shift keying. As you can see, it shifts amplitude depending on whether it's a 1 or a 0. Now let's go and look at frequency. So that was amplitude shift keying. So FSK physically changes frequency. So it's a lower frequency, a lower period for 1s, and a higher frequency for 0s. As you can see, the frequency is higher here, lower here. Higher here for these two zeros, lower here. So you can see it's shifting the frequency of the carrier. So this carrier is physically changing frequency as time goes on and representing this serial bit pattern. Now finally we look at phase shift keying. This was frequency shift keying, and this shifts the phase. So when it gets to a 1 it shifts the phase. When it gets to a 0 it shifts, it's all 0 there, until it gets to a 1 then it shifts the phase. So that's modulating by phase shifting from one phase to another when you change from a 0 to a 1. That's exactly happened for these signals. They only changed amplitude when you change from a 0 to a 1 or 1 to a 0. If you're changing from a 0 to a 0, same amplitude, same frequency, same phase. So that's phase shift keying. Diagrams hopefully explain it maybe a bit more visually. Now we're going to talk about this physical media in a bit more detail. So does physical media have attributes? Is it more expensive? And I'll put some naming conventions in front of you. Has it got a higher bandwidth? Does it suffer, or does interference affect it? Does the closeness of the cables affect it or not? Can you lay them side by side, or do you start getting something called crosstalk when the signals on each cable start interfering? Well, these are some issues which are dependent on the cable, the physical media type, and these are used to transmit data. Different media can transmit data at different speeds. Let's look at some. First one we're going to look at is this one, and that's the cheapest one, the twisted pair, and it's a physical connection. It's probably used in the simplest connection network, an Ethernet, and it basically means you take two insulated wires and you physically twist them together. They're sometimes measured in twists per inch, and to get better quality you have more twists per inch. Okay, so that's a twisted pair. It's the cheapest one, also has lower bandwidth, but it's very easy to fit. This is what it looks like. So here's two wires twisted together. They normally have a twist length, so a number of twists per inch or something, and they're separated by each wire is covered in an insulator, and these are then twisted together, and then these may be bundled together in a set of cables, and then they're installed in buildings. And you might see, but there could be problems with these. We'll talk about those in a minute. So this is a twisted pair cable. Then we move on to the type of cable you might have seen in your old-fashioned analog TV, this type of cable. And this is called a coaxial cable. So this is the live signal down the middle, and it's totally screened by this braid, this conductor, and in between them is an insulator, and then this braid is covered by another covering. So these are much more expensive than these, and they're also much more efficient because basically they're screened, so you won't get as much crosstalk if you put twisted wire pairs together as you would do. Well, coaxial cable should give you hardly any crosstalk due to the way they're physically put together, where the inner is the transmission line, whereas this one of these will be the transmission line, the other will be earth. So this is the earth, the outside shielding, and this is the live transmission signal on this one. So that's two different physical medias. One's cheaper, one's more expensive, one's narrower bandwidth, one's wider bandwidth. One can put moderately high frequencies through, one can put even higher frequency through. Now we move to the top of the range, fiber optic cables. Now these cables nominally transmit light pulses down the cable, and they internally reflect. They normally have a light guide in the middle, some cladding, and then a jacket to try and make sure these fragile light guides don't break. So I've actually got one of those in the lecture I'll show you, which can be used for subsea transmission. You'll see it's pretty physically big and the light guide in it is tiny. So here's 3 different media with 3 different characteristics. The most expensive and the broadest bandwidth is fibre optics. And then we can move on to no cables at all, wireless, which transmits a free signal in free space using electromagnetic transmission of signals. So 4 different types of means of transmitting of information. One of them is wireless, the other 2 are different connectivities but using types of channels or wires. And here's the different types of wireless communication. 2 different types to show you there. Now you might have gathered that this type of transmission needs some rules, some methods for doing it. These rules are called protocols. To be explicit, for transmitting data, they're called data transmission protocols. So they're rules for transmitting information. And it ensures that a number of computers who are connected in this way all know the rules. In fact, they all know the protocols for this particular type of network. So let's look at what these rules or protocols cover. First thing is how the information is put together, what the message looks like. If it's got a start bit, if you remember, we've just seen on our serial sequence of sending digital bits, it had a start bit where the signal changed from a nominal value to another value to tell the receiver at the end, after this low, here comes the signal, if you're running at the right clock rate, that is. So we need to know in these protocols what the format of the message is. The next thing we need to know is where the data is going. What's the address of the computer? And that's the network address. So this is routing information. Then we move on from that to say that, well, how do we break up this information? So how would we break up this page and transmit this? Well, we break it down to a sequence of smaller blocks, and each one will probably have a sequence number to tell you where it went in the page, and these small blocks are nominally called packets. So they're smaller fragments of information. They could be routed separately, but as long as they have a serial number or a sequence number in each packet, you can put this page back together again the way it was. So they're transmitted in packets. So in previous lectures we've talked about this, and we might talk about this more, about how we physically connect up networks in the next lecture in a minute. So we need to share computers via this network, and there could be a number of computers on this network connected by physical media, which we've just seen on the previous page. So here's a number of ways we could connect up these different computers. This one is termed point-to-point, and it's fully connected. This tends not to be used because it's quite expensive. The more computers there are, the more nodes, the more connections there'll be. So we might even work that out in a minute. Whereas this one is relatively cheap, and you could see you could disconnect one of these from this hub and it wouldn't affect the others. So this is actually called a shared communication channel. This tends to be used more than this point-to-point. Now we're going to look at this idea of packets. So a large block of data is broken down into smaller bits. These are actually termed packets. So let's just look at a typical packet system. First, they'll all be switching a particular clock rate. So each one of these will be going a particular time, and each one will cover a particular period when that packet itself is transmitted. The next thing to look at is packets will have addresses. So each of these entities here will have an address, and iconically this is the personal computer end user computer 1, and the packets to it are addressed for 1. And this is end user computer or PC 2, and the packets to it are transmitted to 2. The other thing that you might notice is that you can take different sources of information, so here's some digital lines, and put them together, which is called multiplexing them, and then transmit them as a sequence. And then these will be demultiplexed to the right computer because each one has the correct network address. So that's a particular diagram. The important thing about it is that the information included is really looking at a number of things that are in this packet. First thing that's in the packet is the network address. This network here tells you, network address, that it's going to be sent to this computer. That's the destination address. They might also have in it the sender's address as well. The other thing that it'll have as well, which we're not showing here, is detection of errors, because when you're transmitting it, maybe you don't just send it like this, you send it between different, well, we could call them simplistically nodes, and each node might check to make sure that block of information is correct. So we need some means of checking it, so we have embedded in the packet some error detection or detection of error methodology or information. Now we're going to see how we transmit a data packet. So we transmit a data packet from a transmitter to receiver. The data packet will be placed on the channel and start transmitting, and then it will transmit across the channel and be received by the receiver, and then it's fully received at the end of a particular time period. So we're transmitting a packet. So this is what a packet might look like. So we already talked about this idea of a destination address, and we also mentioned that we've got probably the inbuilt capability to know where this message came from, a source address. We've also seen this idea of a preamble, because in our previous sequential serial bit transmission we have this nominal value which switches down, which says this is the start bit to tell the receiver after this period is a number of bits. So we've got a preamble to tell the receiver that this is a packet of data, and this will be a nominal bit pattern that the receiver knows in advance. Then it will be followed by, and this is an Ethernet data packet by the way, and it's part of the protocols because it's telling you the format of the packet. So we've got a preamble, a destination address, a source address, then length information will tell you how much the length of the data is, then the data itself, and then we've got error checking bits here. So this is really the layout of a packet. So it's an Ethernet data packet telling you how it's laid out as a format for sending the data, and here's the data, and it's got lots of auxiliary information that are needed to where it's going, where it's come from, how long the data is, and this tells the receiver when the packet is being received by the receiver here. You'll first see this preamble, and then when it's been received by the receiver it can check this data with this error bits here. So first, this preamble is used to synchronize the two computers. Nominally it's 8 bits, and it's a particular bit pattern that's been agreed upon for, well, in this case, the Ethernet. Then there's a number of identification blocks, one to where it's going to and one from where it's come from, and then maybe a number of bits of data that tell you how long this actual data is here. So this can be varying lengths, and then finally we're followed by maybe 4 bits to error check this whole block of data here. So that's Ethernet packet format. Now thinking about that, if we think about that, that means that there's fixed overhead for transmitting these. So we've got to receive the preamble, work out the address and send it to the right output if we're looking at a node or a port, and we also have to, if we're checking it, look at the error information and use it. So the reason that these packets are this particular format is because it makes the transmission of smaller blocks of information manageable. If they were too big, you'd tie up the channel for too long, so they had to make them smaller. With smaller units of information, would you have greater overheads? Would you have more of them? Well, maybe not, because it may be more efficient to have them transmitting lots of smaller units. But we just put up with the overheads of needing to require the sequence number and put them back in the right order. The next thing is, this course is not up to telling you this, but actually there was a lot of research done into looking at the size of different packets. What is the most optimum size for a small network as opposed to a wide network? Wider area networks tend to have bigger packets. There was a lot of research done in this. So the next thing that these protocols have to provide is different local area networks or wide area networks will actually have different packet formats. So the one you've just seen, the Ethernet, is for a local, a small network. There's different types of packet formats for wide area networks because they've got to traverse larger distances that are remote. So the next thing we might realize then, due to this linking to wide area nets, is that when you're transmitting long distances, you might need to recheck the message and say, okay, we've come to a break where we've got a number of directions we could go along, a number of different media along different routes. So we might have packets that are temporarily stored and then rerouted. So they could come into a number of inputs, they'll check the address, look it up in a table where it's going, and then maybe reroute it and maybe recheck it using the error coding. So that could be done. So that's other issues that are related to the packet and maybe some rules or protocols that we need to consider when we're transmitting data. So the next thing we've got to look at is normally the name of these sequential channels is called a communication channel, but they're normally shared by a number of other computers. So the important thing to realize here is you don't normally have what's called a tied or dedicated line. That would be very expensive. I must admit, on the side of this course, I once did work for a company that did have two tied lines between its London base and its Scotland base for doing when we worked in the oil business, and they had two tied lines for data transmission, but they were very expensive, so it's not normally done. So one line is normally multiplexed onto by a number of computers. So how does this all work then? So packets themselves are the lowest level of communication protocol. They're the smallest chunk of information, and you can send them across what are called channels, and when you do that, it would appear that you're sending them across a dedicated channel, but actually other computer could still use that same channel that you're using. And when you send them, you don't actually do anything except use particular rules that will change your large amount of data, which could be a block of it, into smaller packets. So the receiver, once it's got these number of packets, can put it all back together in this larger block, and it's a more efficient way to send information by sending it as small chunks which are called packets, and then you reposition the right position using the sequence number, and then you rebuild up the original block of data that was sent from the transmitter. So we've already talked about this implicitly when we've talked about DMA, when it was transmitting blocks of data to different areas in the memory from hard disk or vice versa. So now in your lecture we'll have a break, but now we're going to move on to a bit more connectivity information. One of the things we're going to talk about is this, how you put these small networks together, their topology, how you connect them as a local area network, and you interconnect the nodes and the computers. Well, the first thing to look at is we've already looked at one of these, and this was the point-to-point, which, if you remember, was a fully connected network. And if we wanted to find out how many connections there would be for a point-to-point or fully connected network, this is the equation we would use. And the equation itself is the total number of connections is n times, open brackets, n minus 1 close brackets, divided by 2. So let's look at some examples then. So for n equals 5, this gives us 10. For n equals 10, there's n computers, this gives us 90. For n equals 500, we've got 124,750 connections. So you can start seeing when there's a number of computers, these connections start really getting rather a large amount of connectivity, which may be too many. So this point-to-point connection calculation is n times open brackets n minus 1 close brackets divided by 2, and that's connections, calculating the total number of connections for a point-to-point network. And that's for this network. It's a fully connected point-to-point, so every single node is connected to each other. This one's connected to that one, that one, that one, and that one. Now we're going to name the other network topologies you could have. We've already seen this one, and this is the type of network topology we've already seen, which is a bus configuration where one and all of the system is connected to one single bus. Now this is another type of connection where the signal transmits through the different entities and goes round a ring. Another connection is a star, which might have a pseudo hub in the center. So every connection has to go through the central star connection or hub to get to another one. The other one is irregular, so it would be connected in no real fashion at all. So we have the bus, everyone's connected to a bus. A ring when every connection has to pass through at least one other, or maybe not even one if it's going to its neighbour, but it'll pass through this ring of connections. Then a star, you might have to pass through a hub to get to another neighbour, whereas a regular might have to pass through, well, different routes totally. So we're going to look at these different type of connections and talk about their attributes. The first thing is the ring connection is connected to its neighbour, and that's how it forms a circle of connections. And an example network protocol set of rules that uses this connection is called a token ring. You might guess from that token that something is placed on it and moved from one to the other. We'll see what that is in a minute. The next type of network we've seen before, and that's a bus. We've already seen before when we've talked about processors that this is common to all of its machines that are connected to it. Okay? So we're going to see this is actually the protocols or naming convention used for a bus type of connection is called an Ethernet. So we're going to talk about its rule set or protocols in a minute. Then we've got this star connectivity, which has a central hub, which might be good if you want to disconnect one from the network because you don't destroy the connectivity like you would do with a ring. Then you've got this other one, a pseudo point-to-point, which is actually how wide area networks are connected. They're not anything but irregular connections. Now we're going to start looking at these types of networks and give some metadata about all of them. So the first ones, rings and buses, are actually widely used in local area networks, small networks. They're easy to wire, so you could wire these up with twisted wire pairs. They're relatively fault tolerant, and they transmit data at 10 megabits per second to 100 megabits. So it's relatively fast data transmission, and that's for a bus, whereas a ring network might be transmitting at 4 to 16. So you can see a bus is faster, but we'll see in a minute that the protocols or rules that a buses use are maybe a bit strange, and maybe we'll look at those in a minute. So ring is better over long distances and where heavy utilization of network is required. Now the reason for that is we'll see in a minute when we talk about buses, but it has buses of this type have a very strange way of transmitting data, and it's a bit of anarchy really the way they work, whereas a ring just transmits data from one entity on the ring to the next, and until that's happened no other entity on the ring can transmit data. So it's much more formal, much more controlled, and maybe less likely to have problems. So we'll look at the problems it could have in a minute with the bus, that is. So now in our next lecture, lecture 14, we're going to look at a bit more detail of these different networks. We're going to look at the rule bases of how they transmit across Ethernets and ring networks, and then we're going to look at wide area networks, maybe mention the internet, and maybe talk about layers at the end. So what are we going to talk about? Well, what we're going to talk about in this lecture, the learning outcomes, what we should know at the end of this, is we're going to introduce this idea of these two different connected buses. There's the Ethernet, the bus structure, and the token ring, the ring network, and see that they both work differently. Data is put on these two different entities differently and moved around differently. So we'll explain how that happens. Then we're going to see how we connect these two different entities. Well, if we're connecting token ring to token ring, how do we connect them? And if we connect two different ones in Ethernet to token ring, how do we connect them? So we're going to explain how we connect these either similar networks, smaller networks, local area networks, or different networks together, and we'll have some naming conventions for that. Then we move on to remote networks, larger networks, wide area networks. We look at how we transmit data then. And then we talk about a particular type of transmission, which is how these entities called packets are actually physically moved from the source to the destination, and how they're moved through these subnodes that cover the network, and we'll talk about that specifically. So let's move on to the theory behind these learning objectives for the next lecture. So let's look at these networks. So the first one, a bus network, nominally called an ether network. So how does it work? Well, the first thing is, as it's a bus, everything is transmitted across the bus. Each entity on the bus has a particular unique address, so this could be 1, 2, 3, 4, 5. The other thing is data is transmitted in this, well, I'll give you the name and then try and explain it in the next few slides. It's transmitted using carrier sense multiple access with collision detect. So we're going to see that one of these sends out data onto the bus, and all of the others are listening if they're not sending. So now we've got an enigma, and we'll talk about that in a minute. The next type of bus, which is a ring, is given a particular local area network naming convention of a token ring. This sends information around the ring. Again, each ring computer has a unique number, 1, 2, 3, 4, 5. But it's different to this one. Any one of these can transmit onto the bus. Could be a bit chaotic. This one, if you cannot utilize the token, which will be rotating round the ring, you can't send the data. So you've got to wait until a token gets to you, and then you can pass the data on to the next computer. So we'll talk about the different rules for these Ethernet and token ring now. So let's talk with this idea of a bus, which is actually the Ethernet, and then think about transmitting packets of information across this bus. How would we do that? Well, actually it's got a set of rules to tell you how to do that. The first thing is the packet that's sent is constructed and it will have an address. So if it has an address, be transmitted, and all of these other ones, entities which computers will be listening, and if they don't and aren't that address, they'll be going, it's not for me, it's for me. So this one here will receive the information. Now how does it work though? Well,